So we get to talk about Dr. Debbie's talk on the Lunar Highlands.
Yeah.
You're on.
All right. Thank you, Dr. Britt. So I don't know if there's anyone online, really.
Anyone online? Yeah, okay.
Okay.
But this still made it up on YouTube. So.
Yes. So for those of you who do not know me, my name is Kenny Gordon. I'm a first-year grad student here at UCF. And today I'll just be giving a brief overview of the lecture that was given on Monday by Dr. Brett Denevi. And I also want to just point out, though, that being a theorist myself, this is by no means my area of expertise. So just bear with me as we go through these slides. So in terms of the topics that I'm going to go over today, there are 5 main topics that were given by Dr. Denevi's talk, and I'm going to reiterate those, add a little bit more to some of the topics, and then throw in a bunch of discussion questions just to get ideas flowing for all of us. So the first topic is the different lunar terrain groups. So how is the moon differentiated over time? What regions are there nowadays? Then go more into the Highland crust. How did the crust form? What is it currently made of? On top of the crust, the lunar regolith. How did that form? How has that evolved? Talk a little bit about the Apollo missions, because a lot of the goals of the Apollo missions were to go to the moon, collect samples, and really better understand the geology of the moon. And then finally, talk a little bit more about the polar highlands and how those areas are so much more special than the regular highlands. So when we all go outside and we look up at the moon, the first thing that we usually notice is the face. Those areas of dark and light on the lunar surface. And for the longest time, that was the only way of differentiating the different regions of the moon. You know, so if it was dark colored and smooth looking, it was the mare. Anything else that was light colored, heavily cratered, were the highlands. But now, based on all of this remote sensing data and the meteorites that we've collected from the moon, Jolliffe et al. Has basically split the crust into 3 main terrains nowadays. So we have the Procellarum creep terrain, or the PKT, which is pretty much only seen really on the near side of the moon. We also have the South Pole Aitken terrain, or the SPAT, and we have the feldspathic Highlands terrain. And so a question that has been brought up a lot in this class, but I wanted to ask it again, is what could have caused all of this asymmetry and differentiation on the moon? Why do we only see really the mare and the creep terrain on the near side of the moon, whereas the far side of the moon is basically all highland terrain?
Tides.
Huh?
Tides.
Tides?
Yeah.
How so?
Because
Like the,
it's pulling in one direction.
so why would that pull the
That's
creep
why
and
we're
not the
tidally
highlands?
locked, but
Yeah, that explains why we're tidally locked, but why would that pull just the creep, not the highlands? Or like, how would that influence the magma ocean as that was forming?
Isn't it the Iberian impact that was such a big impact?
Kind of pushed everything to the near side, or?
Yeah, like that's why the near side is mostly mare. It's more impact. Probably does have something to do with tidal locking, though. Why the near side has more impact.
So the near side of the moon is, the crust is thinner.
Right.
And don't quote me on this, but I think it's also, I want to say warmer. Like the temperature gradient is.
That would make sense.
A little bit, yeah.
I think kind of low to the far side.
Yeah.
Okay.
That doesn't explain the creep terrain.
Right.
But it explains, the asymmetry part at least. If one side of the moon was warmer, you can imagine if you have an iron ball with a blowtorch.
Okay.
It's kind of melting out.
It's true.
It's kind of melting and pushing it away.
Isn't the far side more impacted because it's facing away from Earth? And so what if
It does have a lot more
what
impact
if
regions.
there, and what if there is, and then it got covered by other junk?
I don't know if there's real big evidence for that, but that's, I mean, I honestly don't know.
The creep terrain should in general be, I want to say, below the crust.
The
Yes, and I'll go into that in the next few slides,
I
but
had a good slide last time we had a discussion. It showed like how if you have eruptions and you have like a lot of heating, you're pulling the creep up from that
Right.
area, and so there seems to be more mare. That is a good question.
Right.
Why are there more mare on the near side?
right. Yeah, what you just said kind of goes into the next slide where I'm going to try to go into a little more detail about that creep terrain. I know we've gone into detail a lot of times, so I don't expect the slide to take very long. But one thing that I did enjoy was that this is mainly named after the Oceanus procellarum because it's the largest mare that we see on the lunar surface. It's basically all of this region right here, whereas the rest of the mare are just like smaller regions that appear spontaneously throughout that near side. So the creep terrain is about 16 to 18% of the lunar surface, depending on how we define its boundary with the thorium concentration that we see. And again, as we were talking about, this is really the product of the global magma ocean, where the Highland crust did form first, and then the mantle of all of that like iron-rich stuff kind of sank down. And what was left was these incompatible elements and the heat-producing or radioactive elements. And then, yeah, a lot of the mare and the creep terrain. Oh,
Yeah, I have a comment.
a comment?
Or, for when you're done.
Okay, no, that's fine. Yeah, I was just going to say that most of the stuff that we see in the creep terrain are the basalts from the internal moon that has been resurfaced through all of that early volcanism. So bringing stuff up to the surface, as we were talking about, which is why we see that it's very high in iron, titanium, and thorium content. And we also do see in this creep terrain that it does contain materials of both lighter and darker albedo. So the lighter formations are really like the non-mare, which can really attest to the subsurface makeup of the creep terrain, which was likely caused by those large early impacts that also brought more stuff up to the surface. And then those dark regions that we see were really due to those volcanic flows that we talked about.
I have a fun aside. I just Googled Oceanus procellarum because I wanted to check the Latin for translation of storms. And it is the only Oceanus instead of mare because it's the biggest one.
Right.
Mare means sea and Oceanus means ocean. I
Yes.
did not know that. I thought they were all mare, so that's cool.
Yeah. Yeah, and so that's why this creep terrain is named after that ocean that we see, because it's basically everything that we see on the near side is just that ocean.
One other question on that.
Yeah.
So, someone feel free to say if I'm wrong here, but the mare were formed from large impacts which cracked the surface and lava came up, I believe.
Yeah.
That is,
Well,
that's part of the,
Crustal
The surface
softening,
was,
yeah.
I think the surface was certainly cracked by the large impacts.
right.
The issue as to why it's there rather than someplace else, because the whole surface is cracked.
Right.
So
Is the asymmetry in the center of mass, center of figure offset.
I have a fun fact for you that will make you angry. I did a report for Dan's geophysics class on like the definition of supervolcanoes in the solar system, and all of the mare are technically supervolcanoes, and I hate that. So,
Why?
Why? Because supervolcanoes are defined by flow rate, and so like all impacts are supervolcanoes automatically once they get to a bit like
Gotcha.
the point that they're liquidizing things, and that's a bad definition.
There's a lot of bad definitions.
Yeah.
Yes.
In space.
So my thing with that is then, so we already agreed that, I said, and no one argued that the near side is warmer.
Uh-huh.
Right.
So if you're slamming a warmer rock with, let's say, asteroids and comets, other debris of the same size,
Mhm.
you'd expect larger, deeper craters on that
Right.
near side. So I would expect,
That has been covered up by the volcanic activity or.
well, that at least that you get bigger craters on the near side of the moon, which it would result in these mare formations, and maybe not so much on the thicker crust that's on the other side. That's cooler.
Well,
I kind of beg to differ with that because of the next slide, but
isn't it implied that like at least some of these mare are the impact sites because they're circular?
Oh yeah,
Where's that
well,
Yeah.
basically
Yeah.
all of them are.
Do you have that one?
I do not have that, unfortunately.
Oh, I like that picture.
that was a good picture.
So I would think that the near side would have larger craters.
Yeah, I concur. 'Cause-
I mean, I'm just picturing, imagine you have like pavement and you throw a rock at it
Yeah.
versus you throw a rock at warm pavement, like when it's right when it's been paved.
Yeah,
You know, I would expect a bigger impact.
true.
Same energy. I think that would just be another reason for that dichotomy between the two sides.
I don't know enough about impacts to contest this, but I feel like you're wrong.
I was gonna say, I'm looking at Dr. Britt's face, and I wasn't sure whether or not he agreed or disagreed with what Ryan just said.
I could be thinking of something else, but
That's fair.
in this case, I'm not.
Okay.
I think the energy that you're talking about here is way bigger than you can manage throwing rocks at sidewalks. If you could throw a rock at 30 kilometers a second, you would crack the sidewalk. You would break it. You would destroy it.
So you're saying the structural integrity of the material is kind of irrelevant.
Well, no, it's not irrelevant, but it's a question of energy. And so,
You're not doing a phase state transformation when you throw a rock on a sidewalk. When you throw
Well-
an asteroid onto the moon, there is going to be a phase change in at least
well,
part of that.
the issue is this MV squared thing. And so the energy carried by that mass goes way up, way fast. And so you could probably, if you could hurl a rock, say you're a Martian space marine, for instance, and have not just muscles, but have this space armor that amplifies everything. You could literally throw rocks at kilometers per second. Then you're talking serious energy, and you would get some serious phase transitions just by throwing rocks. And I think that's the story here, is that it's actually more or less the only relevant aspect of a solid versus a liquid or soft crust here is the fact that we're retaining the shape of these craters. If the crust wasn't solid, we wouldn't be seeing them. It's just that the really big impacts occurred on the near side. And
Just coincidentally.
well, this is one of these things that I don't have an answer for. There are various theories, but nobody has really given me what I think is a compelling reason why.
The far side does have
Yeah.
darker.
Yeah, doesn't the far side have at least one Mare?
Well, it has small
Mare.
pieces of Mare,
Yeah, very small region.
very small regions. So something like 95% of all the Mare is on the.
Was
right.
it entirely
side.
lost before or after the late heavy bombardment?
Well, I think it was tidally locked pretty early.
Okay.
So
So then wouldn't it make sense that the far side has bigger stuff just because like if the earth is here, then it would be really hard for something to come on the near side. Does that make sense?
well, there have been people who have made gravitational focusing arguments.
Like it.
Because remember, you made the moon 4.4 billion years ago.
Mhm.
And then the late heavy bombardment came by 3.9, 3.8. So 500 million years is even for planetary science, that's a lot.
Yeah.
Yeah.
Wait, I have a question about the mare. So I know they're smooth, but do they have like really thick rims or high rims around them?
The craters, you mean?
Right,
Like the transition between the north and south.
Like the rims of the Mare or something?
Oh, yeah.
right.
Yeah.
There's crater formation. It is crater formation, and so you're getting raised rims and overturned flaps and all the stuff you get with.
I'm just like wondering because if there's the impacts on the near side were so large and had so much energy that all of the ejecta from that, all that rebound, I mean, where did it go? Like,
Went all over the moon.
Yeah.
Everywhere.
So-
have you heard the theory?
so
that,
did it just like, because it looks like they're deeper, in terms of depth, the craters on the far side are deeper.
on the far
Or-
side.
No, well,
Or the
do we-
mare
do you
like
have a
more like
far side-
shadowed?
do you have a far side image?
The only real far side image I have is either this one or the one.
There you go.
Oh,
All right.
nice.
So I mean, yes, there are like small regions of mare that appear. This actually right here, I was going to talk about on the next slide. This is something entirely different.
Yeah,
But,
but you don't have the same level of huge impact basins
Right.
that you do on the near side.
So my question is, are the mare really, really deep in like comparison to the craters on the far side?
Well, they're bigger craters, and so they're
So they
deeper.
are.
But the mare is not covering. The mare itself is relatively thin,
Right.
at a planetary scale. You know, it's kilometers deep,
Right.
but it's still fairly thin. So it's basically a hydrostatic thing that you're filling up these craters to a certain level, given the available basalt and the available force pushing that basalt out.
Could it be something like the first big impact was on the near side, so the crust is weaker there?
Well, all of these are good questions to ask Dr. Neal on Monday.
All
So
right.
you'll be talking a lot about the mare.
Because his topic is the mare, and
Right.
one of the first questions that you should throw at him as soon as he starts talking is, why are they where they are?
Okay.
And
Would you like us to interrupt the speaker more with questions, or?
well, that would be fine if you
Okay.
have interesting questions. Please interrupt the speaker.
Okay.
That's why they're there, and you're here. And you're not shy about interrupting me, so why don't you?
Yeah, but you're physically here, and I can tell by your face that you don't mind most of the time. It's much easier.
Well, but they're a long way away, so they're not going to like whack you with a ruler. You know, the whole effort here is to squeeze information out of these people, and
Yeah.
when they need to expand on something, you know, please give them that opportunity.
I'll try and do that more often. So.
And Clive is just a gentle and accommodating soul, and so he'll be happy to do that.
All right. So yeah, so that other region that we saw on the far side, down near the South Pole, is the South Pole Atkins terrain, or the SPAT. And this is unique because it contains both the highest, or at least some of the highest, and some of the lowest points on the moon, going up to about 8,000 meters and down to about minus 6,000 meters. And so the prevailing theory is that this was actually formed by a giant impactor, but a very slow giant impactor. And so that would explain like why it had such high mountains, but at the same time, these really deep ridges. It has moderate levels of thorium, as can be seen from this image down here. So not as much as the PKT, but definitely more than the Highland terrain, about 7 to 14 weight percentage. And again, Joliffe et al. Classified this as a separate terrain, basically based on these 6 different reasons. So due to its high average iron concentration relative to the non-mare lunar crust, also because of its large diameter, this is actually one of the largest impact basins in the solar system. And it also occurred early on in Moon's history, and had a great effect on the subsequent thermal evolution, and especially in the upper mantle section, where the impactor struck specifically. It also occupies a very broad region of that extreme topographic depression, and as well as the mountains. So that kind of like differentiated it from the surrounding terrains as well. And then, despite what we were talking about earlier with this like thinning crust and its depth, there's been really no significant resurfacing of the salts that have occurred. So this further supports the slow impactor theory. But what's also interesting about that is that the thickness modeling indicates that there is significant crustal material present below the basin floor. And it shows that the impact, even though the impact would have evacuated well into the mantle and sunk really far down, that crust is still pretty thick below the basin floor.
Do you know what those colors mean? The circles?
It's a topographical map.
Yeah, this is just
Yeah,
topographical.
but do you know what the circles are?
Red is high.
No, but
The big black circle is.
Oh, the big black circle versus
What about
the.
I think those are
the
different
light pink
ridges.
circles?
Yeah, they're
So
different
ring-
ridges.
Different rings of the South Pole. It can,
Right.
I don't know how much you know about crater
Sorry.
formation. So with initial craters kind of carve out a cone into the ground, and
Right.
when you look at them over time, they get eroded.
Yeah.
Bigger impacts get a peak in the middle, and then bigger impacts, that peak becomes a ring.
Right.
And then eventually you can get multiple rings coming out
Okay.
with larger craters.
Yeah, so
I'm not 100% sure, but that's
No,
That's right.
that's right. So they're basically just the rims of
it's
the.
just weird how they're kind of concentric, but not really.
Yes.
Probably.
Well, remember that the shock waves of this are sloshing around the entire body.
Right. So
And
even though it's
this-
really slow, it still forms a lot of those rings.
Right, and this impact is a major percentage of the size of the radius of the body. So you're gonna, and if it's differentiated, you're gonna get all sorts of weird reflections. So yeah, often it is symmetrical, but it doesn't have to be. You can think of all sorts of reasons.
We're talking about those big rings.
Yeah.
Right. The black and then the like smaller pinkish and then even that purple ring.
Is the sort of like line of pinkish circles, are those like other craters that happened later on top of it, or are they related to the?
Which one do you
Oh, I
specifically
think those
talking
are-
about?
In the circle.
I think
Yeah,
those
in
are
the circle,
Like these ones here?
points.
Yeah.
those
they
are
kinda make a line.
craters in a crater.
Okay, so those happened later and are unrelated?
Right.
Okay.
Well, that's why South Pole Lincoln is hard to see.
Right.
It was the first big basin that has survived enough to see.
Right.
There might have been a bunch of other big basins that essentially got erased by crater saturation.
Like that video you sent us.
And so, well, I shouldn't say saturation, equilibrium.
Equilibrium. Crater destroyed from crater.
And in fact, South Pole Lincoln wasn't actually noticed until like the 90s.
Right.
Because it's on the South Pole.
No, well,
It's not
we
one
didn't
of
have
those.
that good of imagery of the whole moon. And so when we got better laser altimetry, we noticed that there was this low spot,
Very low spot.
very low spot, that didn't particularly look like a crater unless you stared at it for a long time.
Right.
People started staring at it for a long time and started drawing these concentric circles and said, oh, crater.
How low is it relative to the rest of the moon?
So it's about 6,000 meters below just like the average level. So the surrounding highlands is actually about 10 kilometers below the surrounding highlands. It is very shallow,
That's big.
or very deep, sorry.
Sarah, you had a question?
But if you zap back over to the whole moon picture.
So it's very hard to like actually tell
Well, it's
that it's
darker.
that deep.
Kind of, or is it the screen you're viewing?
Well, it is actually just a tiny bit darker.
It is very slightly darker, but
It's
it's
easier
still
to see on the TV.
There's a
actually yeah. This one over here,
Yeah.
it's kind of easier to see, but
Oh.
yeah. So that's why, like Dr. Bridge said, it was very difficult to find.
Sarah, you had a question?
Yeah, I don't know a ton about impacts, but is there like
Neither
a
do I.
a generalized principle, like if it's a slower impact, like that's a huge impact, like it's moving slower, it's a bigger one, it's moving faster, it's a smaller one, or is that just this kind of garbage
It's
idea?
just energy.
Okay.
It's a function of the mass and
Yeah.
So if
Yeah.
you want to get the same size crater,
Yeah.
you either have to have a lot more mass or,
A lot
A
quicker.
lot faster.
Yeah.
well, not a lot faster because it's this V-squared
Oh,
thing,
yeah.
like physics.
Somewhat faster.
A little bit fast.
faster.
Yes.
Yeah, I think that they're basically saying if it was a really large, it would have melted more things. It would have flowed back in.
Well, it's hard to see because remember that this thing then gets subsequently beat up because you're talking the rest of the Mare or the rest of the late heavy bombardment was about around 3.8 billion years. South Pole Aiken was about 4.1.
Right.
So 200 million years doesn't seem like much, but you can get a lot done in 200 million years.
The solar system was a busier place back then.
Yeah, and this is when the impact flux was trailing off. So anyway.
All right, and then the last of the three main terrains is the feldspathic highland terrains, or the FHT. So this is about 4 to 6 weight percentage of iron, which reflects that high plagioclase content that it has. Very low thorium content, which is, again, consistent with that magma ocean theory of the less dense cumulus kind of rising up, whereas everything else sank down. So it is the largest terrain, as we were saying, by area and volume, covers about 60%, if not a little more, of the moon's surface. And again, as we were saying, it's mostly on the far side. It's characterized at the surface by that high albedo that we see to give it its light color. Lots of rough terrain and very cratered over millions of years. Elevated from the surroundings due to that low density and no real volcanic activity in the highlands. And then, of course, there's large amounts of feldspar. And then this image I found really helpful and interesting. This is a cross-sectional view of what we believe the highland terrain looks like. So we have the central anorthitic region represents the thickest part of the lunar crust, goes down to about 70 to 90 kilometers. And judging by the makeup of the lunar meteorites that we have, it's composed predominantly of that Faroan anorthosite.
So how do you tell if a rock is a Faroan anorthosite? By a glance.
Right.
So you don't have geochemistry, you don't have isotopes, you don't have X-ray diffraction.
Can you pick it up and it's heavier because it has iron?
Well, actually, pick it up, it's much lighter. But what is
Darn.
That's honestly what I was thinking too.
It's really, really
Answer.
bright. White.
Yeah,
white.
light color.
Yeah.
Exactly, it's
Okay.
bright white. You don't get that many really bright white rocks in geology.
Okay.
They get gray or dark very easily. This stuff is bright white. If somebody hands you a rock, and it's mostly dark material with a bunch of white fragments in it, that's probably a lunar meteorite, because you just don't get that anyplace else. And people who look at lunar meteorites can tell these things at a glance. That has to be a lunar meteorite.
Why don't we really see it anywhere else?
Well, how many magma oceans do you have in the world?
Touche.
You actually do have a few.
Yeah.
You can go
Right.
to the Stillwater complex in Montana and Idaho. It's under 8 feet of snow right now, but it's still, it's a refreshing trip.
Okay.
And you'll be able to see this kind of magma, large magma differentiation settling and rising.
Would like the Mid-Atlantic eruption zone also be one of these places?
The mid-ocean ridges?
Yeah.
No,
Okay.
because what you need is a big chunk of magma that cools slowly.
Okay.
And what's happening at the mid-ocean ridges is the crust is thin. You're pushing molten material, partial melts through the crust at a rapid rate.
Okay. So like, what about like somewhere around Iceland? That's
Well, Iceland, no. Greenland, yes.
Okay.
Siberia, yes. A few places in the Himalayas, yes. But that's about it. You just don't get much. What you need is a big intrusive puddle of magma, tens or hundreds of kilometers in diameter, at some depth in the crust, and then you need to be patient. You need it to cool over millions of years. Otherwise, you're not going to get this kind of settling and floating
So
stuff.
it's just typically it's being recycled too fast to cool into this.
Yeah, in the mid-ocean ridges and in places like Iceland.
Did I steal your question, Kiana?
No. So the Mare is the fast cooling, and then the Highlands is slow cooling. Right?
Well, yeah, if you want to look at it that way, the Mare erupted out on the surface, and the Highlands basically formed from the entire thing was molten, and you created stratification, and you got a quick cooling on the very surface, but below that it cooled much slower over millions of years. And you ask, well, where's the surface today? But of course, it got beat up by impacts and went away. And so this is another characteristic of planetary science. If you can't figure out what happened to something, just say impacts. Oh yeah, late heavy bombardment wiped it all out.
All right. Thank you, Dan. All right, so getting more into the crust mineralogy, this table that I found basically gives the percentage of the different main types of rocks that we see, as well as the oxides that are found in those rocks. So, as we were saying, lunar highland crust is very ancient, billions of years old, really. This is the accepted age. And again, that represents the crystallization of the anorthosites from that lunar magma ocean. And the upper crust is very plagioclase rich, and evidence from the composition of the uplifted central peaks of those craters indicates that this composition does extend out to at least 30 kilometers away from all the craters. And then, as Dr. Denevi said in her talk, there are basically three main groups of crust material that everything can be put into. There are, as we were talking about, those Faroan anorthosites or fans. So this is the main thing that we're going to see on the surface, that white material with the very high albedo. And most of these rocks are over 85% volume plagioclase, and some of them are even up to 99%. And they are also very rich in calcium, and they are what form that flotation crust of the magma ocean, but has been beat up over millions of years afterwards. The second main suite is the magnesium suite. So these are the magnesium suite and the alkali suite occur in a lot lower percentage of the lunar crust than those fans. The magnesium suite contains a lot more diverse groups of rocks that are all really mafic. So they have the higher magnesium percentage, higher magnesium number, rich in pyroxene and olivine. And then the alkali suite are the more alkaline plagioclase, the more sodic, and they are very creep rich. So a lot of those that we find are found near that PKT region that we discussed earlier. And these include basalts, granites, some of the anorthosites, and the gabbroic norites. And the alkali suites are the ones that are very common in the craters that we see, being brought up by those large impacts. And then talking more about the regoliths. So when Dr. Denevi gave her talk on Monday, she referenced basically like 3 different definitions of the regolith. And the most current definition said that it's more of a philosophical thing than anything because there's no clear bedrock layer for a reference. And I was wondering, why is that? Why is there no clear bedrock layer for the reference of the regolith?
There's a book in my office that's that thick, and it's the Glossary of Geology. And if you look up bedrock, it says that it's a coherent rock strata or surface. If you look up regolith, it is the fragmental layer that overlies bedrock. So the reason you can't find bedrock is that you beat the whole surface to hell. And actually getting down to something that's not shattered, you're talking kilometers, many kilometers.
How large does a piece of rock have to be to count as bedrock then?
Oh, that's a philosophical discussion. I'd rather not.
It's all philosophical.
Well, you know, you can have, bedrock is basically still attached to the rest of the body in some coherent, solid fashion. Now, what we term as bedrock is, of course, floating upon a semi-molten asthenosphere and mantle and moving around. So fixed is not really, is a relative term because all bedrock is moving around on Earth. So once you get to something that's not pervasively shattered, that would be bedrock. So bedrock is at the surface in many places on Earth, but on most planetary bodies, what you get is pervasively shattered material. So piles of rubble on top of something that might be more coherent, or piles of rubble with nothing more coherent. That's just
So it's just because we don't really know how far down that regolith goes that we.
Well, yeah. Well, we do. We have seismic information, so we know that eventually you get down to something that's fairly coherent.
Okay.
But the thickness, it depends upon your philosophic approach to regolith versus bedrock.
Okay. Thank you. So regolith can be generated from a bunch of different scenarios, mainly from the impacts that we see on the lunar surface. Those impacts can be from all sizes. So the early bombardments and those big impacts, those are really what created the kilometers of the mega regolith that we see. So the regolith that's basically all the same material stretch out for kilometers in directions. Whereas the smaller and more frequent craters that we see a lot of the times form those finer grains and the larger differentiation between different regions of the regolith. And the regolith can also be caused or generated by thermal fatigue and temperature cycling. I am not very familiar with those terms, and I was wondering if we could talk about the ways that the regolith was generated from thermal fatigue or temperature cycling, really.
So you have a piece of rock.
Right.
So how can you what are the ways you can break that rock?
Smash it?
You can hit it with a hammer, yes.
Yeah.
What's another way?
Heat it up?
Heat it up and then drop it in liquid nitrogen. Would that do it? Yeah. So that's thermal cycling.
Okay.
So you do it repeatedly and it keeps getting smaller and smaller.
Okay.
Thermal fatigue. Well, that's essentially the same thing. Why is it breaking when you're heating it up and then abruptly cooling it?
The rapid temperature change.
Well,
that happens,
rapid,
so.
But if the whole thing was a single material and has the same coefficient of thermal expansion or contraction, why would it break?
Because it doesn't.
It's not
It
all the
doesn't,
same.
yeah. It doesn't.
Okay.
So ergo, this rock that you're picking up is the same thing through and through.
Okay.
So the answer is yes or no. Is it the same thing through and through?
No.
No.
Right. So, that's
So it's made up of all sorts of stuff that have different coefficients of thermal expansion. So if class X is expanding a lot faster than class Y class, it's gonna push on that and fracture it. And that's why these things break.
Awesome. Okay.
And you don't have, and you don't have to do it. You can do it that way in the lab, but on the surface of the moon, how hot does it get during daytime?
A couple hundred Kelvin.
Now more like a couple hundred centigrade. Then it goes down to like 100 Kelvin at night.
Okay.
So you get 300 centigrade swing.
Right. So that causes a lot of the.
That could cause a lot of stress.
Got it. Okay. Thank you.
Plus, you're whacking it with things all the time.
Right. Which goes into the next comment about all those craters helping to cause that scattering and the reworking of the regolith surface. And so we do find that in the Highlands, especially on the far side, for craters that can get up to pretty big, so to about 50 kilometers, they are actually in equilibrium. So one is destroyed for each new crater that is formed. And that has altered the regolith of the Highlands significantly over time. And then, as we talked about on Monday as well, the strength and the direction of the impactor can lead to that surface asymmetry that we find in the regolith out to tens to hundreds of kilometers from the crater center, as can be seen in this image here, where we see these kinds of bands of all of the ejecta material being stretched out very far from the impact. All right, so getting more into the Apollo missions. So Apollo 14, its destination was, it tried to go to the Highlands, it failed. It went to the Fra Mauro Highlands, which is kind of the Highlands, but it's actually still part of the creep terrain, so it's not the real Highlands that we classify according to those three categories that we mentioned earlier. But it was classified, or did have the success of being the first mission to land in rugged terrain. And it did bring back a lot of important rocks and samples that we find. About 42 kilograms collected are the breccias, so the rocks that are composed of fragments of the other older rocks, which is why we think that the landing site is part of the ejecta from the Imbrium Basin, which is very close to where they landed. And many of these breccias, as we
Can I just correct you real quick? Breccia.
I'm sorry. Many of the breccias include material that is enriched in that creep, which is why we were able to figure out that they landed in that creep terrain and not the actual highlands.
So could there be actual highlands underneath all that ejecta, that creep ejecta?
For sure, yeah.
Say, only a kilometer or so down.
Right.
Which of course, it could be 10 meters or it could be a kilometer. It doesn't make any difference. You can't access it from where you are.
Right. So, so maybe that the reason that they found all those materials was just because of that ejecta. And then just a question that I thought was kind of interesting. Since Apollo 14 ended up going to the landing site that Apollo 13 was destined to go to, where do you think Apollo 14 would have gone otherwise, other than just saying, oh, it would have gone to the Apollo 15, which would have gone to the Apollo 16, which would have gone to the Apollo 17. So like, where else do you think?
You have one more lunar mission. Where would you put it?
Yeah, basically. Where do you think it should have gone?
Let's go back to the image of the moon.
Image of the moon?
Okay.
Far side. That weird.
That's what I'm thinking.
Far side.
Well,
that was one of my follow-up questions on
have-
a later slide, was like, why haven't we gone to the far side yet?
Well, you have limitations. You can't go to the far side because you can't tell. You don't have
The satellite communications, yeah.
And you can't go farther south than that, or farther north than that,
Why not?
because the engineers tell you that, and they run the program.
It's just orbital.
Can you
patterns.
Why do the engineers not want to go to the poles?
Yeah.
Well,
Orbit
it's.
insemination.
Well, they do, but they didn't back then.
The issue is really delta V. It requires more energy to plane change.
Mm.
And they just didn't have that energy designed into the Apollo landers. All they were really interested in doing when they designed the landers was to get down to the surface and plant a flag. And they said, oh, well, while we're here, maybe we should collect some
Like some
rocks.
stuff.
And they finally, toward the end of the program, they actually took someone who knew something about rocks. They took a geologist. But there was only one.
Schmidt.
Yeah, Schmidt.
Why there?
Because this is different than all the rest of
I think one of the missions was down in the
But
region.
it was
Yeah, I
like
think-
on the edge or something, right? It was
Yeah.
like
Yeah, you're right. It wasn't like smack dab on the
far
flat
enough
surfaces
that
here.
ejector wouldn't
Did
have
any-
covered.
Yeah.
I mean, this is a more difficult landing, but there's like this little like fake mountain ridge.
Kind of
No,
like
they landed
over
on
here.
Yeah.
Well, yeah,
that was
they
one of
actually
the-
landed.
Yeah, they landed there. That was the next one that I was going to talk about, Apollo 15, or it's
I remember
16, one of
thinking,
the two.
wow.
I used to
Yeah, I
know
think-
are all the landing spots were, but I have
Well,
forgotten.
she had that
I
map.
think
I know, I'm
17
sorry, I
actually
didn't know that.
landed about here.
I'm sorry?
Did 17 land about here?
Yeah.
I did not look into 17 that much.
Well,
Yeah.
One
one
of them landed
further
there.
down than that then. The very furthest we could possibly go.
What about that bright spot?
The engineers will not like you then.
Well, not further,
They'll
but I know
start-
what I'm
they'll
saying,
start-
within their
There's
limits.
like a
You
crater,
said they
there's
make you
also
go
like a bright
stop here, so
spot.
let's go
Yeah.
right
As far down south as you can go.
Anicia, point at the bright spot.
That one?
Yeah. What
Yeah.
about that? Did we go there? That
No.
looks different.
It does look different. It's a nice fresh crater.
Yeah.
There would be compelling science that you could do there.
Yeah.
The engineers would hate you because you'll have lots of fresh ejecta.
What if we landed far away and we just pulled in the rover?
Well, far away is a relative thing, you know.
Far enough away
Far
that
enough
engineers
away.
stop yelling at me.
Well, that's
So
a
you're
big
gonna
crater.
walk
Let me
the
do my
Pine back
research.
for 3 days.
So
and then
you
you're gonna
have to
a road
expect
trip.
that
Yes,
the,
that's a sweet road trip.
that the thick ejecta blanket will be at least 1 crater radii out.
Mm.
So you're talking a lot of kilometers.
For size reference, the spat is 2 Texases across. So this
Can't go there though. To be
No, I'm saying like that right there
Yeah,
is 2
2
Texases.
Texases,
So if you want
okay.
to park far away, that's
So
like
it's
a
like
whole
Alaska.
Texas away.
Right, yeah.
And
This,
road trip,
this
you're
right
going
here
1
is
mile an hour. pretty much.
2,600 kilometers.
Build
Yes.
a lander that's mobile, that has a mobile part that detaches the whole thing.
That's
and
they
it's
drive
traveling.
This whole conversation is in the Apollo era.
Mhm.
No, we're talking now though.
Whatever,
You
yeah,
know
that's,
how
that's
long
what I
it
was
takes to
like.
drive across Texas when you're going 80?
Apollo region is-
Well, yeah, my question was like, why didn't they go to the
Taking a
far
road
side? And
lane
I
would
understand
be
that.
much slower.
Yeah, it was mainly because of the satellite issues, but
Oh yeah, if you go to the far side.
yeah, you're not
no
going to
one
have
can
communication.
I would
Yeah.
sign
So-
up for a 3-day there, 3-day back road trip on the moon. Just
I think it's
saying.
more than 3 days.
Fuck
I would sign
This
up
is a-
for a
I
10-day
mean,
there,
they were
10-day
only
back road trip.
they were
on
only
the
on
moon.
the surface for what, 3 days?
Yeah.
Yeah, maximum of like 72, 73 hours.
Yeah.
Yeah.
So I mean,
Why don't they?
go there and then leave. We got here, now go.
Why don't they just? Again, I don't really understand like how because we can't go to the far side because we couldn't communicate. Yeah.
Yeah.
Can't you just put? I understand it's not a Wi-Fi hotspot, but a Wi-Fi hotspot, if you know what I mean, like
Yeah.
on the
That's-
near side.
That's one thing that I was
and then
thinking
you
of.
just like go to the far
Well,
side.
That's one thing that I was thinking of.
Satellite.
Why didn't they?
Satellite, and
Yeah,
then
they had the
satellite.
orbiter, so why
You
didn't
need
they
the
just send communications to the orbiter?
Well,
That's
the
my thing.
orbiter is actually kind of low. You need something that's high enough
Okay.
in orbit so that you can see the lander
Yeah.
and the Earth
Earth.
at the same time.
Yeah, can we just do
Why don't-
it?
yeah, why don't we
They're trying to
No.
build like a
Yeah,
sunshade
like,
for
I think that
exoplanets. I
like-
feel like we're
Like not in the Apollo era, but is
But
that
that's
reasonable now?
Yeah, that is reasonable now.
They
Where's
want
the
to
Yeah.
use that.
That's what gateways
Put
were.
them in orbit.
Frank-
They
Oh,
can-
really?
Yeah.
Okay.
Where's
Yeah.
that?
And I was going to talk about that in the later
All right.
slides as well.
So let's get back to,
Yeah.
Do you know
um,
where they landed on the far side? The Chinese lander? The
no,
Near the
offhand.
north. Yeah. I'm not
Is it
exactly
like
sure.
our spot
It's
that
near
we're
the
interested
dark
in?
Far
on
enough
south side.
north to irritate.
I
things.
think.
Well, they landed in a pretty flat spot.
Yeah.
that's
Okay. So I think that they landed right around like up here.
Oh, wow.
Yeah. I could be wrong, but when I looked at it very quickly last night when I was looking at why didn't we land on the far side,
Is it the Lunar
think it was right
rover or am I crazy?
I don't know what it's
person?
called.
I forget.
Call it the Chinese thing.
Yeah.
It's not like they have a whole bunch.
It's almost certainly not how it's pronounced, but is that anywhere near how it's spelled?
So yeah, so then Apollo 15, the main objective of that was to sample around the mountains that we talked about earlier. So they did like that region of the mountains that was like kind of going down in like a J shape. They did actually go there. It was expected that this would provide material from deeper in the lunar crust than what was sampled in Apollo 14. And then it also provided them an opportunity to explore Hadley Real.
Yeah. Sweet.
Which was a channel in the Mare surface that was probably formed from volcanic processes, so they were expecting to get a lot more of that volcanic material. This does mark the first Apollo mission to bring back the first anorthosites collected directly from the Highlands, so not just like that ejecta from Apollo 14. They brought back a variety of magnesium sweet rocks as class in the Brescia. And this was what I thought was pretty cool. One of the first of what was called the J missions, where they have those 3 to 7 hour long EVAs would be performed, and then this is the first one that marked the lunar rover on the surface. So it allowed them to travel much larger distances, collect a lot more. And then Apollo 16, they were directly in the Highlands, which was very nice. They were able to study 2 formations. Descartes Formation, which is hilly, and the Cayley Formation, which was relatively smooth highland plains. So they did actually land in somewhere that was relatively smooth. And it was important because these 2 formations cover more than 10% of the lunar near side. So it was very important for them to actually go there and be like, what are these? Prior to the mission, why they wanted to go there, it was thought that both of these would have volcanic origins. However, the return samples demonstrated that that was actually incorrect. Cayley was more of the impact deposits from the Imbrium ejecta mixed with the local material during the impact event. But they did get very large samples of anorthosite collected, like we were talking about earlier, very bright white rock. And we already talked about that question.
I'll put in, I looked it up. The current Chinese lunar rover is the U2, Y-U-T-U.
U2, yeah, something like that.
Yeah, so.
Yeah.
Not the thing I said earlier.
No. Okay, so going more into the polar highlands, why these are important. They contain a lot more of the craters with those PSRs, the permanently shadowed regions. So even though they have near constant sunlight, they don't really reach the interior, and so these craters are very important because they contain that fossil record of the hydrogen, water, ice, and other volatiles from the early solar system.
Question.
Yes.
Okay. This class is about resource utilization.
Yep.
And the resources we would like to utilize are the volatiles and the stuff in the PSRs, right?
Yeah.
But
Correct.
then we just said that the engineers don't let you do this. So then,
Well, those are the engineers in the Apollo program.
okay,
And
was
so
50
we have a
years
new
back.
set of engineers now.
okay,
And all of them agree that we have to go to the poles.
okay.
And that
Because
is
if we
addressing
don't- If we don't go to the poles, then the Chinese will get there first.
Spat.
Hell yeah, space race.
Yeah, there
Yes.
we go. The Chinese
Um,
landed in the spat.
But yes, Anicia, what you just said is true. The sampling would be important, very exciting.
Okay, just
Um,
checking that we're in the course of
Yes.
class.
Bringing it all back.
Yeah, so the base material that we find in those polar regions are still the highland material, but they do have a lot different formation histories because of like the sunlight and the where they're located on the lunar surface. And then the North Pole is different from the South Pole in that it contains a much lower quantity of those PSRs. So it still has a lot of craters, but not as many of them are sheltered. So in this image of the water ice that has been found at the poles, we see the South Pole has a lot more water ice centered right around the actual pole, whereas the North Pole still does have water ice seen around, but it's a lot more spread out. And I think these images.
Well, you need to be careful using the word found and has.
Well, I guess
Just
predicted or
predicted
yeah.
and speculated.
Right. And I think these go out to about 70 south/70 north. Could be 60, I forget. But yes, the lunar polar regolith has much less of those basalts and accrete components than the Apollo 16 regoliths. And so, question that we were kind of going into, what are the pros and cons? What would they be of living at the poles? You know, they might have that water and the volatiles, which would be very helpful, but what else makes them so like, we should go there or we shouldn't go there?
We should go there to collect what we want and then leave.
And leave.
Yeah, because the poles are very cold, aren't they? And not an ideal place to plant yourself.
I mean, the average temperature is around
Does
60.
temperature really have that much of an issue when you're in a suit? There's no atmosphere.
I was just saying, even still, the temperature is still around like 260. I think I lost that. Yeah, approximately 260 Kelvin. So
But we're not saying the permanently shattered region. We're saying the polar region in general.
Well,
Right.
yeah.
right, yeah, that is the polar region in general is about
But
260.
also,
Because the shadow regions would
if you have a good amount of insulation, it may make sense to put it in a permanently shadowed region because then you don't have the thermal stress on your
Mhm.
structure.
That's
Like,
true.
in
You don't
terms
want to
of
stay on the
psychology,
near
but
side
Wouldn't it
where
screw
you're
up your
constantly exposed to
We don't care about
Right.
people's mental
If
health.
way
you put
higher
a
degrees.
space station inside a permanent shower region, someone's gonna murder someone.
I mean, people go in nuclear subs for how
Yeah,
long?
I mean, you
6
just need
months,
those.
yeah.
You need those nice
And
solar
the
lamps
International Space
somewhere with
Station
like a
for a year.
garden, so you can go sit in the garden and be like.
More than a year.
Well-
Psychologically, that's a
He said
terrible decision.
living.
Yeah, he said
Would it be hard?
Yeah, living at the poles.
Yeah, that's why I was like,
Yeah.
We should go.
Permanent-
We should be,
permanent
no,
settlements
no,
was
we
the
should be
question.
slightly
So,
off of it.
I would say the major problem is you don't have solar power.
That's also a great
That's
point.
gonna be.
But you could just make solar panels around the permanently
Yep,
shadowed
that was
region.
addressed in one of my next slides also.
Otherwise, you'd have to bring some kind of maybe like a fission device or something.
I mean, you should probably have that too, just in case. Like,
So you would be able to get the taxpayers of the United States to give you 80 pounds of bomb grade U-235.
And we can shoot it off in a rocket, why not?
Tiny ones on it.
No, they have, they use just plutonium, so they
and
just
we're,
use heat from the stuff.
and we're out of plutonium now, right? Even for
No,
mass
there's
emissions.
lots of plutonium, you just have
Well,
to
wasn't
make it
there-
every now and then.
Isn't it like the UN doesn't want us to make any more plutonium though, and so like NASA got a certain amount and we're running out of it fast?
No, well, what happened was that
I don't know if that's
there's
possible.
there's several isotopes of plutonium. Some are really good for making bombs, and some are just,
Radioactive.
well, they're all
We're
radioactive.
all radioactive.
Okay, for the gloves.
And you just
Sorry.
you just get decay,
That's not what I meant.
and what you want from the decay is to be nice and toasty.
Yeah.
And U-230 plutonium U-238 is actually really nice for that. You make the bombs with another isotope of plutonium. The thing is that in prior years, when we had a big nuclear weapons program, you got the RTG isotope of plutonium as kind of a byproduct of your weapons production. Since we're not as crazy as we used to be and don't make nuclear weapons with wild abandon like we used to, there's less of this byproduct around. And you have to actually go and make some specifically for this application. And it used to be that the Department of Defense wanted a bunch of this for their own sinister reasons. But they don't do that anymore.
I have a feeling they're about to.
Space
Well,
Force.
Well, that's a whole other conversation.
So how many hoops do the military have to jump through to get like a nuclear sub for that reactor?
For the reactor,
Yeah.
go to Congress, you ask them for money.
So you think that'll be that much more difficult for NASA?
Yes.
Yeah.
Yes.
Well, the thing is with a nuclear sub, you're buying the same U-235 or whatever fuel mix you have, and building a fission reactor. in a place where they've done that since the 1950s. What you're talking about with building an entirely new technology in fission reactors designed to operate on the moon, and then shipping it to Cocoa Beach, and launching it over the heads of 20 million registered voters in Florida.
Why not?
Could you maybe set up a refinement plant on the moon? And
No.
Okay.
Why?
That was a very
Refine-
quick.
Well,
Is it just too heavy to transport, like
Well,
heavy
what-
water?
well, no, it's with uranium, what you do is you take uranium ore and you extract the tiny percentage of it that is U-235. So, you're throwing away, I forget the percentage, but something like 99% of the uranium. The way you do this these days is centrifuges, high-speed centrifuges. And so there are these big plants with vast numbers of high-speed centrifuges. Because the difference between U-235 and U-238, for instance, is tiny. And you essentially have a cascade of these things. It takes a lot of energy, takes a lot of mass. In the old days, you needed an industrial plant that took like a quarter of a square mile. Jeez. So you can go look at it right now. It's at Oak Ridge. You can take tours.
I've done that.
Yeah. Big building, isn't it?
Yes.
You definitely, they really, you
What's the one
can't drive
across
on the
the
wrong place where they get really angry.
Yeah,
when
well,
you
they
come
get
in.
angry for the most trivial reasons.
Yeah.
What's the one across the street with what's it,
The Y12.
Y12? Yeah, we almost got shot there.
Yeah.
Well, but, it's not like they use it
They're
anymore.
very angry.
They're machine
Oak Ridge
guns.
if you drive on the wrong area.
It's
Yeah,
snipers.
well,
They're supposed to have someone come meet you at the gate, except sometimes if you're a bunch of undergrads, they don't, and then they're really angry that you got the wrong direction.
So I think we're getting off onto a
Yeah,
very
sorry.
long
so
tangent.
my point is that actually making it on site is not an option.
Right.
And it's not that big a deal to build a fission reactor, power reactor, and put it on the moon. It just takes money, and whoever is leading the project just has to deal with the Greenpeace demonstrators that chain themselves to his front door every morning. That's part of the landscape.
All right. Well, that discussion was good because that leads into the next topic of actually going there. So the Artemis mission, I'm sure you all have heard of, its next crewed spaceflight mission or spaceflight program. The goal is to land the first woman and then the next man on the moon by 2024 and actually establish sustainable, constant exploration on the lunar surface by 2028. So they are trying to scout lunar resources, in situ resource utilization, and perform a bunch of different science experiments on the surface. And the first destination that they've decided is actually the lunar South Pole. Due to the abundance of water that is predicted, at least, to be there, because this does provide the best resource for the prolonged human exploration. We can get drinking water, we can get the water to cool down equipment, we can get water to turn into breathable air, and then we can also use the water to actually make additional rocket fuel when necessary. So we kind of already discussed this question as well. Where do you think they should go in addition to or instead of the South Pole and why?
North Pole.
North Pole.
Also has water.
Let's go explore that bright impact area. That would be sweet.
But
I
takes
really
a
want to
long
go explore the
way.
Highlands. I think we can get a lot more. We can figure out a lot more about the Highlands if we actually go to the far side and land there.
Lava
Yeah.
tubes could be interesting.
That was another
Yeah,
category.
that'd be good.
So here is the proposed mission, the full program out to 2024. So starting this year, they're expecting to have early South Pole missions. Not sure if that's going to still happen or not, but they want to send the first robotic lander for the ISRU, and they want to actually try to get accurate measurements of those volatiles, of the predicted amount of water in those poles. We have a bunch of the different Artemis flights themselves. So the first human spacecraft to get to the moon, the first humans to orbit the moon in the 21st century. And then this actually goes through the production of the Lunar Gateway, which is going to be basically the moon's version of the ISS. So we're going to be able to use that to kind of like propel astronauts forward and farther.
That's cool.
Yes.
I like how Mars is in this picture.
Right, because that's the ultimate goal.
It's looming.
So yeah, they actually put that in there, and that actually goes into like why they chose this to be red. Is actually going to Mars. So there's a bunch of like why they like chose this specific thing. So you have Artemis, like the arrowhead for the goddess Artemis. You have like the moon. You have the red for Mars, the Earth.
Red path to Mars.
Yeah, the red path to Mars. So,
Oh, that's really good
and
design.
they decided to go. And what's interesting also is that this goes the opposite direction of the crosshatch for the Apollo missions to show that we're going in a different direction now.
Wow.
Yeah.
Also, I don't know if everyone knows,
That's
but
a
like,
lot.
Artemis is Apollo's twin.
Yeah.
Yes.
I was always angry it was the Apollo missions and not the Artemis missions. Like, what are
Well, there we go.
What kind of
Now you're
mythology
getting the
are
twin
these
sister in
people
there.
reading?
And she's the actual goddess of the moon, whereas Apollo's the god of the sun. But whatever.
I mean, we can't go to the sun. Once.
So yeah, the last main slide, well, I have one other for final question, but the last main slide is about those lunar resources that we were talking about. You know, the moon bears substantial resources that can be exploited with these future missions. And Ryan, what you were talking about, like the solar power, we could actually probably get the solar power around the poles. There have been talks about extracting oxygen and hydrogen from the regolith, utilizing the water and the water ice for various purposes that I mentioned on the previous slide. A lot of different minerals. So one question was, is it more important to go somewhere that is not full of ejecta, so that's very pure in one type of mineral? Or would it be probably better to actually go to a source that's full of ejecta to sample multiple different minerals at once, in terms of like the lunar resources?
Depends entirely on your research focus or
True.
your economics focus.
True. But
I mean, if you're building a base, wouldn't it make more sense to go somewhere with ejecta so that you're not like you need lots of different things
Yeah.
to build
true.
your moon base?
Yeah.
But then eventually you can just have a mine at like each pure mineral thing.
Yeah, eventually,
Yeah.
sure, but like to start with.
Yeah.
But it's like what you said, like it depends on what your economic focus is.
Yeah, I
Economic
agree.
and
I think
science
the
goals.
impacts are the first place that you want to go to get resources because they have all of them.
I think there's also an argument to make is how much better is landing there and looking at minerals
Right.
versus a satellite, because one is, at least in today's day and age, a lot cheaper.
Yeah, that's true.
You know, if you can get an accurate map to, let's say, 100 meters
Mhm.
just from a satellite, versus you can land and get it, you know, a meter. You know, if the 10-meter one is good enough,
Mhm.
then you can go into specific places.
True.
Once you know that.
And then, yeah, that question that we had earlier, should we try to mine lava tubes for gold? There are predictions that there are gold to be found in all of these lava tubes. And also,
why,
it could actually
why do they think there's going to be gold in lava tubes?
and
Bringing
It's
stuff
pressure.
up from the
Yeah.
center.
Oh.
Because, yeah, anytime you have volcanic eruptions, like you find peridots on Earth around volcanoes, and you find sometimes a lot of rare earth elements or minerals around volcanoes.
Do you find gold around volcanoes?
I don't know where you find gold
Yes.
besides them hills.
Gold.
Yes.
So I know that lava chambers mix up material, and then water gets in there and it can extract material. But that's when you find it in like a river or a
But
crack in a
how-
vein.
right. That's what I was thinking, was like the rivers and how it relates
Is
there.
there any volcanic activity on the Gold Coast in Africa? Because there's certainly volcanic activity on the west coast of the U.S.
Well, there's what drives mineralization
concentration.
is concentration. So the way you get gold is essentially you have fluids that are heated by igneous activity.
Mhm.
But volcanoes themselves and lava tubes. I don't know anybody who has become rich digging around Hawaii, which has lots of volcanoes and lava tubes.
True.
They have a
For
Paradise
gold.
Beach though.
They do.
It's
The
cool.
lava from a lava tube
I've
on the
been
moon
there.
would be closest to what type of lava here?
Well,
Do we know that answer?
that would be the reason you have really big lava tubes on the moon is that since you don't have water, the lava has to be a lot hotter and more viscous in order to melt and come out to the surface.
So that would be more like Hawaii.
So it would be a lot more like Hawaii.
Nice.
So what mineralization is associated with ultimately is scavenging all the gold and heavy metals out of vast amounts of rock and concentrating them in places where you get chemical or temperature change in those hydrothermal fluids.
Okay.
And so it has almost nothing to do with the lava itself. The lava is a byproduct of the fact you've got heat.
Okay.
So why people would think there's gold in lava tubes?
Sounds like something that you would put in your proposal so that someone would give you
Yeah.
money.
Ooh, gold.
Yeah.
Not a bad idea.
It's a
Well,
Still had it my finest.
it's sexy science.
sexy science, yes. Well, no, it's sexy, but it's not science.
Okay, fair enough. It's a
You need to have actual facts if you want science.
I'm sure there is a paper somewhere that says
Yeah.
there is gold in lava.
Well, there's also papers that say unicorns are great mass transit devices because they don't poop and you never have to feed them. And if we had unicorns, that would be great. However, we don't. So the basic premise is false. And they're not going to be a significant foundation of a non-polluting mass transit system. Same thing with gold and lava tubes. I am at a loss to think of any concentration mechanism that would deliver a reasonable amount of gold to any of these lava tubes. The fact that you have hot rock is not enough. It's the same, probably the same people that say they're solid platinum asteroids.
oh yeah.
All the way through.
Yeah, people have actually gotten up in public and said that. And I've gotten up right after them and say, "You're wrong. There are no solid platinum asteroids. There is no evidence for this. If you have any evidence, I want to hear it now."
Google said that it just brings it up from beneath the surface to the surface.
Well,
Near volcanoes.
So
What
maybe
would-
it's
Right, so maybe
separated.
not like in the lava tubes themselves, but like around it. Because
Well,
said you can
what's the
find
mechanism for concentrating the gold?
What about density?
Yeah, that
So
would
have
make it
a
sink,
Thin
wouldn't it?
layer
But then the
at
lava
some
pushes it
point.
up.
Yeah, and so if
The
you-
lava pushes, yes,
Yeah.
but why wouldn't it just sink to the bottom of the magma chamber?
I mean, theoretically, yeah.
This is the problem
Theoretically,
with
yes,
Googling
but-
stuff.
I was gonna say, I apologize. This is
Still be-
also just
It's like
rumors that I've heard.
No,
So
this is a good combo stuff.
The short answer on mining lava tubes for gold is that nobody has ever seen any gold in any lunar samples or lunar meteorites.
touche.
Not
Probably
promising.
shouldn't do
So it's
that.
not promising.
Okay.
All right.
Is there any, what's the carbon content of the moon?
Not very
Yeah,
much.
so I was gonna say diamonds could be something, but
Not really.
No.
Okay, so then just some final questions. We're running a little short on time now. So basically, in what ways can like findings of our own moon lead to discoveries on other solar system objects and satellites? For example, Io, we know experiences those extreme tidal forces. And since we talked about the thermal fatigue, do we expect to see similar regolith on Io? I mean, obviously it's very volcanically active, so I don't know if that would have any influence on seeing that regolith or not, but anyone any ideas or?
That's a cool question. I don't have any comments. I just really like it.
Is the moon closer to Io or closer to like Mercury?
Mercury. Well, oh, sorry, I thought you meant physical distance.
But like, in terms of what it would look like.
I mean, Io is the most volcanically active
Body in the solar system, yeah.
Changing.
I would say Earth is probably most
I mean-
close to Io based off.
Mercury.
I think
It's
it's
just-
I think it's like Io,
Yeah.
Earth, or
Are the rocks on Io being recycled fast enough that you wouldn't necessarily see them at like the end stage of being broken up?
that's true. I'm not
I
sure.
mean, Io,
But the-
Io doesn't have any craters, so I would say the surface is pretty new.
Yeah.
Right, I mean, it's
It's
constantly
recycling
being
itself all the time.
renewed and
Mhm.
resurfaced. So because of all the constant volcanic activity, it's changing very rapidly over time. So it's true. And then
So the answer to that question, I'd say no.
no,
No, I
Okay.
would not see similar regolith on
I think
Io
it's
as I do the
different.
moon.
that's true. But then do you think that any of the other findings that we found on our moon or that we will find on our moon can lead to discoveries on other solar system objects?
Do any of the tidally locked other moons have the same weird asymmetry that our moon does, where like one half looks completely
good
different from
question.
the other?
I don't know.
What is like Iapetus?
I-
It's got the equatorial bulge.
Maybe, yeah.
But I mean that's asymmetry, but not.
Isn't
Right, not
Sharon
like the-
tidally
yeah.
locked to Pluto?
But it's
Yeah, I mean, I would-
dichotomy
It is.
south.
Yeah, I would have to
It's
say
a north-south, but that's Pluto's dichotomy, not Sharon.
No, Sharon's
Plu-
south.
Is
Sharon's
Pluto tidally
north-south,
locked with it as
okay.
well?
So no, but
Could
not.
it have
close.
been the other way around and then gotten knocked
Yeah,
over?
knocked over like Uranus.
Is there? I don't know if there's like a big crater that says it would be knocked over. I don't know what it looks like.
I don't know. I don't think so though.
Yeah, and Sharon's also probably a more recent addition to the system than the moon. I don't know. You're the Pluto expert.
They're
So
so
say dance the Pluto.
they're so close in
He's
size.
saying the land when we say something obviously wrong.
And there's
Not-
evidence that Pluto's like pole has changed to line up with Sharon, but I don't think there's anything that says Sharon got knocked.
I'm definitely no Pluto expert, but like, I would think it'd be hard for Pluto to capture Sharon. Like, the Earth couldn't capture the moon.
Well, when you're that far out, things are going hella slow.
Okay.
Very slow is what I meant to say.
Is I was like, is the distance between Pluto and Charon changing like Earth and the Moon,
Yes.
or is it stable?
I think it's
If they're
stable.
tied-
See, it's coupling between the oceans and the moon and the Earth's rotation.
Would we have that precise of data to determine that? Just real quick. Fly by it. Because we're only moving by what, an inch per year?
Yeah.
A few inches per year.
The moon moves away as fast as your fingernails grow.
Yes.
I think you're the one that told me that.
You're
back
welcome
then.
for that. All I remember from Master 101.
All right. That's basically all I had.
So, what are the resources available from the lunar islands?
Creep. You can mine the regolith for oxygen.
I don't know, because she put that slide up and it literally said creep oxygen question mark.
And then it said
The
structures.
targets of opportunity.
Oh, yeah.
You know, the regolith in the Highlands could maybe be used as an insulating material. The regolith itself could potentially eventually be useful. I talked about my crazy Discovery Channel show.
Oh my
that made solar panels out of
Death
regolith.
ray.
So maybe
Excellent.
regolith itself is potentially a resource.
Well, sure. You know, regolith is full of silicon and oxygen.
Yeah.
But the Highlands is not really a wild menagerie of precious metals.
Yeah.
That was my comment after last.
It's
class.
It seems like the moon is more, if we want to mine things on there, it's stuff you can take to a moon base and make that more economically feasible, but definitely not anything you want to bring back to Earth.
Yeah. If you're going to the Highlands, you're going to it for the polar water.
Right.
And pretty much nothing else.
But that's important.
And
Which is why
yes,
Artemis is going to the moon. It's just mainly for the water.
right. And the whole point to emphasize is that when you're going to the poles, what you are not going to get is the mineral sweets that you find in the Mare.
Right.
Because you're not on the Mare anymore.
Pretty much the farthest you can be away from the PKT.
Yes. Yep. And that's a useful point to make to people who have illusions about what they'll find. Anyway, thanks, and we'll have Clive Neal talk about the Mare. Don't forget to ask him why it's there.
Okay.
Thank you, everyone.
Thank you. That was a really good presentation.
Good job.